All right, so this is the second part of the lesson on hypothesis testing, in which we continue the idea of the hypothesis test from before, but look at a couple of new ways of testing data, and it depends on what we're trying to test. So last time we're looking at the chi-squared test, which is ways to determine if there seems to be dependency between sets of data. And the next one I want to look at is the chi-squared goodness of fit test, which is used to determine if the observed values, how closely they relate to the expected values of some sort of distribution, and how if they are deviating from that farther than we would expect. For this, the idea of degrees of freedom, which will come up more in the course later on, is something that we didn't have to think about last time we want to talk about here. But again, the best way of approaching these is to look at some examples. So we have a 6-sided dice that's rolled 100 times. The results are shown in the table. So you can see 1 came up 10 times, 2 came up 18, and so on. And we want to determine if the die is fair. And so we want to come up with an hypothesis. Then we're going to use this chi-squared goodness of fit test, which I'll talk about, and then determine with a critical value of chi squared being 11.07 if we think this dice is fair or not. So first, let's make our conclusions, which again are the null hypothesis. Sorry, we don't make our conclusions. At first, let's make our hypotheses, which are the null hypothesis and the alternative hypothesis. So the null hypothesis is the default position, where in this case, is that the dice is fair. The die is fair. However, how are we going to assess that? Well, in this case, if the die is fair, then each result should have an equal probability. So I'll say all results should have an equal probability. Keep in mind, that doesn't mean all results will be equal. They should just have the same probability. So that's the null hypothesis. The die is fair. The alternative hypothesis is the complement of this, which is the die is not fair, which would mean not all results have equal probabilities. And so again, the two hypotheses should always complement each other. There should be no room for some middle ground. It's either, in this case, all results have equal probability, or not all results have equal probability. All right, so in this case, we're told to use the chi-squared goodness of fit test. So we have our observed results here. We need our expected results, which in this case, if the dice really is fair and you roll it 100 times, then we would expect a 1 to come up 1/6 of 100 times, because there's a 1 in 6 probability of a 1 showing up. There's a 1 in 6 probability of a 2. Each one of these has a 1 in 6 probability. Do that 100 times, we would expect 1/6 of 100, which is approximately 16.666. I'll just leave it as a fraction. So the expected results for each of these is 100 over 6. Those are expected. Write this in a different color. I should have given myself more space. So every single one of these, if it really is fair, the expected value for each will be the same. Although again, that doesn't mean because I see different values here, this dice is not fair. We are always aware with probability, there's, a perfectly fair dice can lead to different values showing up. Over time though, it should get less and less likely that that's the case. The more you roll, the less and less likely it is that we'll have vastly different results. Because right now we do have some pretty big differences, 21 to only 10. However, it's hard to tell if that really means anything or not. And that's what the goodness of fit test can tell us. And so, again, this is where you have to use your GDC. But in general, in most GDCs, you go to your stat and make a table in which your first column is the frequency, and in this case, the frequency of our observed results. The second column is our expected. And you type that in, and then you perform the goodness of fit test, in which there's 2 statistics we want to pay attention to. However, one of the things it will ask us are the degrees of freedom before you can calculate anything. And while we'll talk more about this in later lessons, at this point, the degrees of freedom is always 1 less than the number of categories. In this case, the number of categories is the number of results possible. So there's 6 possible results. The degrees of freedom is 6 minus 1, which equals 5. You'll have to tell the calculator what your degrees of freedom are. Once you do that, you should get 2 statistics we're really interested in. The chi-squared, which is approximately 4.76, and the p-value, which is approximately 0.446. Now, with that said, if I look at the question, it was stated in that we weren't given a level of confidence for our probability. So while this isn't meaningless to us, we can't use it for our conclusion, because in advance of performing the test, it was stated that we were just going to focus on the chi-squared value of 11.07. So although I will say what this is telling us is that, I think in a percent, this is roughly 44.6%. So you can imagine this means if the dice is fair, a result like this we would expect to come up almost 45% of the time, which right there tells us that's not a small probability. There's actually a decent probability that this would occur purely by chance, almost 50%. But I can't use that just because we have to go with what we decided on before we performed the test, which is the chi-squared value of 11.7. Well, we have a chi-squared value of 4.76. And again, remember, this is a measure of how far our results stray from what we'd expect. This strays less than our confidence level. And so our chi-squared, 4.76, is less than 11.07, which means this does not exceed our threshold. This does not meet our threshold, which means I cannot accept the alternative hypothesis. We do not have evidence that this dice is not fair. It may still not be fair. We just don't have enough evidence to say with confidence that it's not fair. If we had a chi-squared value more than 11.07, if it strayed more than that, then we would have that confidence. And so with that said, I now need to say that we fail to reject H naught. So we don't say we accept H naught, because it's still, that null hypothesis that the dice is fair may still not be true. We just don't have evidence of it. So we can't reject it. We say we fail to reject H naught. And I'll say we have not enough evidence to decide the die is unfair. And in general, with all these hypotheses tests, we either fail to reject or we reject H naught. Again, it's all binary. It's one or the other. And keep in mind, if we were given the probability, we'd have to decide what level of confidence we'd be okay with at the beginning. I said in the last lesson, quite often it's 0.05. This would far exceed that, which means, again, we would probably just reject this anyways. But again, we should always have that critical value, whether it's a probability, which is the most common, or in this case, a chi-squared value. We always need to have that in advance. So that's always decided in advance, which, keep in mind, is a bit subjective, which is why statistics, as mathematical as it is, has a lot of subjective aspects to it. All right, I now want to talk about a t-test. And a t-test, maybe I'll look up here. A t-test is a way of comparing the means of independent groups of data. And they have to be part of a normally distributed population. And so for a t-test to have any validity, we have to have 2 sets of data which are independent of one another and are normally distributed. And if we look at our means of the data, we can use a t-test to determine if the difference is a matter of chance or if it represents something else. So here's an example that's real. I had 2 different pre-calculus 11 classes, block A and block B, in a row. They wrote the exact same test on the same day. These 2 classes typically have a similar average scores and variances on their tests. For my B block class, though, there was a lot of noise from the neighboring class, and the students seemed to be distracted by the noise from next door. And I was curious if this affected their results. I did notice the class average for block B was lower, but that alone doesn't mean it was because of the noise from next door. So here are the results out of 30 possible marks for both the classes. So yeah, it's a lot of numbers. These are all the test marks out of 30 for one class, and these are all the results for the other class. This is the class that had some distractions going on. The question is, was that distractions enough to explain potentially the difference in the mean? I will say, there's 25 students here, there's 24 students in this class. It doesn't matter, they're different. So I want to now, assuming a normal distribution, so assuming that our marks are normally distributed, I want to come up with an appropriate hypothesis test to determine if the noise from the B block led to that lower class average. And I want to use a 0.1 level of significance, okay? So with that said, the first thing I want to do is make my hypothesis, and we start with our null hypothesis. And the null hypothesis is that there is no significant difference between the means. And so in this case, for this, I'm going to call this first group, I'm going to call this, I'll use mu for mean. I'll say mu A is not greater than mu B, because again, that's what I'm trying to look at. Now, just because the average is bigger doesn't mean we've proven anything. We're trying to see what's the probability of the average being bigger, which we'll get to. So that's my null hypothesis. My block A is not greater than block B. And then my alternative hypothesis, which has to be everything else, in which it would be the average, my mean A, is greater than this. Right? List A and list B. Now on my calculator, I don't have list A and list B, I'll have 1 and 2. So you may want to think of this as 1 and think of this as a 2, because on most calculators, they differentiate it like that. So how do I determine this? Well, I want to use a one-tailed test. I use a one-tailed t-test. And let me talk about what that is. There's two types of t-tests. A one-tailed t-test is in which we're just concerned if looking at the probability of one average being less than or greater than the other. And that's what we're curious about. I'm just looking at the probability of one average being greater or less than, one of the two. A two-tailed test, which is not what we're looking at here, is in which it doesn't really matter if it's greater than or less than, we're just looking at the probability that they're not the same. And again, the means will probably not be the same, but we're looking at the probability of them being different by various amounts. And so a two-tailed test is just seeing if they're different. Doesn't matter if it's greater or less than. A one-tailed test is more specific, less than or greater than, which is what I'm trying to see here. Does my block A class, does the first mean, is it greater than the second by a significant amount? At this point, we need to use our GDC on most GDCs, and I apologize, there's a lot of data here. I just wanted to include it all. You'd make two columns, one with the 25 marks here, one with the 24 marks here. And you want to find a two sample. So generally we use what we call a two sample t-test. And you need to be familiar with your own. And then pretty quickly, it should tell you, and we want to choose, we're trying to find the probability of this occurring. We want to find the probability that, in this case, mu1 is greater than mu2. And you should get a p-value of approximately 0.119. And again, all the work I just mentioned is, you need to be clear with your GDC. It's not difficult, it just takes a bit of practice. And again, we're setting up for this. We want to find where the probability that mu1 is greater than mu2. All right, so what we get, this value here, notice is greater than my level of significance, which means the probability of these means being different, the probability of my A block having a higher mean than my B block it's too likely to be a matter of chance for me to say the difference is because of the class next door. We don't exceed this level of significance. And so I'll say since 0.119 is greater than my level of significance, we fail to reject H0, the null hypothesis. We don't have enough evidence to conclude the difference was not just a matter of chance. So again, it doesn't mean we now know for sure it was the differences has nothing to do with the noise. We just don't have enough evidence. And until we have enough evidence, we have to, we fail to reject H naught. We have to stick with that null hypothesis, the default hypothesis. All right, so for this last question, looking at a trial of a drug designed to decrease blood pressure. And we have a group of 10 patients, and they have their blood pressure measured at the beginning and the end of the trial. And so person A had the exact same blood pressure at the beginning and at the end. Person B went from 141 down to 135, and so on. So we want to see, is there evidence at a 5% significance level that the mean blood pressure is lower at the end of the trial than before? Assume that they are normally distributed with equal variances. And again, to use a t-test, we have to assume, and we should really only use a t-test if we know the data has a normal distribution. So with that said, similar to before, I need to make my two hypotheses, and I always start with the null hypothesis. The null hypothesis is that this drug will not significantly lower the blood pressure. And I can say that by saying mu1 will equal mu2. Because if the two averages are the same, it's not made a difference. And again, at some point, we're gonna think about the average of these compared to the average of these, or the mean of the start compared to the mean of the end. And so the null is that this is not going to have an effect. The null is always the default position that it's not whatever, in this case, happening. In this case, it's not going to be effective. And in this case, that means the mean is the same. My alternative hypothesis is not just that they're different, is that this is going to be greater than this. Or perhaps, to be honest, I really should actually adjust my null hypothesis. Instead of saying they're equal, I should say that U1 is not greater than U2, which could mean they're equal, or it could mean that it's less than. All right, so by saying mu1 is not greater than mu2, that covers everything. So notice there is no other middle ground here between my two hypotheses. We either have the average greater or it's not greater. Right, we covered everything. So again, since I'm concerned about if one is greater than the other, we want, again, a one-tailed test. So use a one-tailed t-test. And similar to before, we want to find the probability of this occurring. We want to find the probability that the starting mean is greater than the ending mean. And you should quickly get a probability of this occurring, at our p-value, and our p-value should be approximately 0.0365, to three significant figures. So since we wanted to pay attention to a 5% significance level, what I have here is less than that. So since 0.0365 is less than 0.05, that means the probability of this drop being purely by chance is smaller than our threshold, which means we have enough evidence to reject our H naught, because there seems to be even a smaller probability of this occurring by chance than we were willing to accept. And that means I can say we reject H naught and accept H1. Oh, not high, H1. Or I can say that, which means that there seems to be evidence that the drug does reduce blood pressure. And so, according to the t-test, which we were told to use, and the threshold, we've exceeded the threshold, we seem to have evidence to reject the null hypothesis. However, to finish things off, it can be argued, in fact, it really should be argued, that a t-test is not appropriate for this data. And so why? Because we statistically found something that seemed to show this drug lowers blood pressure using the statistical analysis. But when I say it can be argued, perhaps I really should say it should be argued. And so why? And the key, if we go back here, we should only really use a t-test when we have independent groups of data these are not independent. By that I mean your ending blood pressure is definitely related to your starting blood pressure. The two are not completely independent of one another. And that makes a big difference. If these two sets of data are somewhat dependent on each other, and they definitely are, your final blood pressure is somewhat dependent on what your starting blood pressure, then we should not use a t-test, which means really this wonderful work we did is not valid. And really, we shouldn't really use a t-test for this, not with the way the data was laid out, because again, my two sets of data were not independent. And so, as I'll write here, a t-test requires that both data sets be independent of one another. Now, in terms of an IB assessment, that means if we were given a question like this, there have to be some way of working with the data differently or using a different test, because in this case, a t-test gets us a value, but we really shouldn't use a t-test on data that's not independent. And we really want to remember that. It has to be normally distributed, although it says right here, assuming it's normally distributed with equal variances, but it also has to be independent. And again, this data is not independent. And I'm done.